everybody, and welcome to my presentation. It's a big pleasure to be here today. So when we want to generate new molecules that have targeted properties, we need to navigate huge chemical search spaces. And among all of the methods that exist out there for doing that, genetic algorithms have been really popular over the last years and even decades. They're popular for several reasons. Two of them are that they're really easy to configure to different targets, and they don't require any gradient information for the optimization. How genetic algorithms works is that you start off with your molecule in a population. You do some property evaluation, traditionally done with density functional theory. And then from these energies, for example, you get some fitness, how well your molecule is suited to the task. At the end, perform some crossover and mutation operations. Then you end up with a new molecule population, and you iterate this over and over until at the end you get some optimized candidates out. Genetic algorithms have been around for a long time, but they've risen in popularity in the last few years because they're really easy to couple with supervised machine learning, and this evaluates the main bottleneck in the optimization pipeline, which is the density functional theory calculation. However, in practice, when we want to do some optimization procedure, there is often two settings that we want to steer towards to. One is an exploitation setup where we stay close to the training set. We get some very nice predictions, but maybe don't move so far away from the training set. On the other side, there's the exploration case where we move away from the training set, discover new materials classes, but might risk some inaccurate predictions. Unfortunately, the conventional machine learning-driven genetic algorithms, I've introduced them on the last slide, don't have any balance between this exploitation and exploration trade-off. So they can't control the proximity to the model applicability domain. Let me illustrate this with an example. We do our optimization, and at the end we get some candidate out that has some very nice machine learning predicted properties. We might look at this molecule and think, how well is it now characterized by the machine learning model? Did we stay well within the model applicability domain? We have accurate predictions, but maybe didn't move so far. Or are we really far out of distribution? We can't really control this in our optimization procedure. So this is from a more methods perspective what I want to introduce in my talk here. Uncertainty-aware genetic optimization, which can balance or control this balance between the exploitative or the explorative setting. Of course, when we want to do some optimization in practice, it's better to have a real challenging optimization target and not only stay with toy optimization targets like is often done. So what we focus here is Singlet Fission, which presents a promising route to increase the efficiency of solar cells. How that works is it doubles the photocurrent from high energy photons. And Singlet Fission is very interesting to look at from an optimization point of view because there are only very few Singlet Fission classes known. So these ascenes that you see here below, they've been really studied for a long time. But apart from that, there's maybe 2 or 3 other classes that are known to exhibit Singlet Fission. You also have multiple hard to fulfill objectives on your excited state energies that aren't so prevalent if we just look at a random molecule. And historically, the optimization procedure for Singlet Fission has just been exchanging some substituents on these ascenes. So we really need to discover some new classes for Singlet Fission. Here, I want to show you a quick outline of what I'm going to talk about in the next few minutes. In this project, we started from experimental crystal structures and then did 2 things with this. We devised a diverse fragment pool for the genetic algorithm and then did machine learning for excited state properties. We brought these 2 things together and performed our uncertainty-aware optimization. And then in the end, I'm talking a bit about the chemical insights that we could gain and some nice singlet fission candidates that we found. From the method uncertainty-aware optimization, we again start off kind of from the usual genetic algorithm pipeline. Now we have a multi-objective optimization hierarchy for our target. But the main change that we do is our property evaluation now gets replaced by multiple machine learning models, where you do multiple predictions and get a calibrated uncertainty from that. In a bit more in detail, we do kind of very standard procedures, so test time, data augmentation, bootstrapping, and combining different molecular representations to get this calibrated uncertainty. So this means that the prediction uncertainty, the standard deviation which is get from these multiple predictions, corresponds to the prediction error on our search space. So if we have large uncertainty, our molecules are likely to also have a larger error. And then we kind of modify the fitness determination of our genetic algorithm. So per molecule, we do multiple predictions and then get our performance value rho that you see here on the right side. So rho equals 1 kind of means it's a good, well suited to our singlet fission task. Rho 0 is just not very good at all. And because we have multiple models with this calibrated uncertainty, we get multiple performance values that could either be close together or be a bit further spread, depending on how certain our machine learning models are. And because you now get an average and a standard deviation, you can employ, for example, the confidence bound that you might know from an acquisition function in Bayesian optimization in our genetic algorithm setting, and either be in an exploitative case where we discourage our uncertainty, or we have mu minus 2 sigma, or we could be in an explorative case, mu plus 2 sigma, where we promote our uncertainty. So when we move through this optimization loop at the end, we don't only get candidates with a desired property, but we also get a targeted uncertainty. Again, if this was a bit too convoluted, the important thing is that we change our fitness function to include the uncertainty, either in an exploitative or an explorative fashion. In terms of the nice chemistry that we discover here, we start off with the exploitative case where we discourage machine learning uncertainty. What we discover here is we rediscover known singlet fission materials that have a high occurrence in our data set. So the ascenes that I've highlighted here with this, oh, you can't really see this on the projection, too bad. But the ascenes, we've seen them before with these fused rings that have a really high occurrence in our data set. And so they're predicted with high accuracy, aka low uncertainty. We also perform some local optimization on the substitution effects, where we can show that the substituents that we add actually improve the singlet fission propensity of these ascenes. On the other hand, when we move to the explorative setting where we promote some level of machine learning uncertainty, we discover a variety of chemical motifs that have never been looked at for singlet fission, but show very promising properties. And this is what I want to focus on for the next slide, where we discuss, okay, what chemical insight can we get from these candidates? What we discovered are these donor-acceptor configurations with the donor shown in gray and the acceptor colored in red. And these show excellent excited state properties for singlet fission. And this is very cool because at the moment we only have a very, very limited pool of donor-acceptor combinations for singlet fission. So it's very valuable to kind of add to this pool of known chemical substructures. In particular, I want to highlight these red acceptors that we have here, these mesoionic acceptors, so mesomeric and ionic, that have 3 adjacent heteroatoms next to each other. And these are very nice properties, some nice triplet localization in the excited state. And because they have an already established synthetic route, they might be kind of within the synthetic reach for experimental validation. So to summarize, why should you care about what I've been talking about in the last few minutes? If you're interested in the chemistry and the application, we've presented singlet fission candidates that have very nice properties, and these are promising for further computational or experimental investigation. If you're more interested in the methodology, we've kind of extended the usual genetic optimization pipeline to two different settings. An exploitative one for local optimization where high accuracy in your optimization pipeline is key, and an explorative one that you could use to avoid reconvergence on already known classes, for example, in an active learning setting. So to bring this all together, I think this is a very broadly applicable framework that can be used for a variety of molecular design tasks. And with that, I want to thank you for the attention and everybody that worked on this project. Shell Jorner at ETH, everybody at EPFL, Terry Blaskowitz, Rum La Plaza, and Clémence Cormain-Boeuf. And of course, if you have any questions, I'll be happy to answer them, or chat afterwards. Just write me an email if you want to discuss further. Thanks a lot for your attention.